Alright, yo, it's William Wu, and I'm gonna do a tutorial on second order linear differential equations with physics. But before we get to the physics part, let me first introduce second order linear differentials themselves. So basically, by definition, a second order linear differential is an equation with the formula as shown here. However, most of the time, because we can assume constant coefficients, which is a p of x, q of x, and r of x, we can use the following equation instead, which is also known as a homogeneous linear differential, which follows this format here. So the primary method that allows us to solve homogeneous second order linear differentials is we need to find solutions, two solutions, y1 and y2 of the equation, and then we can plug it into the general solution, which is y of x equals c1 times y1 of x plus c2 times y2 of x. So that will also be a solution for all and any values of c1 and c2, which will be given like as an initial condition or so. And also, every homogeneous linear second order differential has a characteristic equation that we can use to determine the equation's roots. Most of the time, it's going to be ar squared plus br plus c equals 0. Once you solved for r, the solutions will follow the format y of x equals e to the rx. So let's do a basic example first. So determine some solutions to y prime minus 9y equals 0. So without using the characteristic equation, we basically need to find a function whose second derivative is 9 times the original function, such as e to the negative 3t and e to the 3t. Therefore, because y of t equals negative e to the negative 3t and e to the 3t, it follows that the general solution will be y of t equals c1 times e to the 3t plus c2 times e to the negative 3t. We can also use a characteristic equation. In this case, we must solve for r squared minus 9 equals 0. So r equals positive and negative 3, and you get the same answer, basically. Now, let's go to springs. First, let's recall in the work unit we briefly discussed Hooke's law, which allowed us to calculate the force of the spring with the spring constant and the displacement, where f of x is the force, k is the spring constant, and x is the z displacement. Please note here that because the force is opposite of the spring, because the force opposite of the spring is equal to kx, the restoring force of the spring is going to be the negative component, negative kx. So next, recall that Newton's second law states that force is equal to mass times acceleration. So first, because force is opposite the direction of displacement, you can set the two equations equal to each other in order to get mass times acceleration equals negative kx. Now remember from basic position, velocity, acceleration, that acceleration is the second derivative of time. So therefore, we derive the second order linear differential in the following format. The mass times essentially the acceleration is equivalent to negative kx. Now that we understand how the second order was derived, let's try an actual example problem. So let's say a spring of a mass of 2 kilograms has a natural length of 0.5 meters. A force of 25.6 newtons is required to stretch it to a length of 0.7 meters. If the spring is stretched to 0.7 meters and released with an initial velocity of 0, find the position of the mass at any time t. So the first step is we need to calculate the spring's constant. So by using Hooke's law, k times 0.2 equals 25.6, we can solve for k, which equals 128. Now we can plug k and the mass of the spring into the derived differential equation. First, we get 2y double prime plus 128x is equal to 0. In the case of the spring, we have a special characteristic equation that we use to account for the spring constant and mass. This equation is also shown here as x of t is equal to c1 times cosine of wt plus c2 times sine of wt, where w is the frequency, which is calculated by the square root of the spring constant divided by the mass, and c1 and c2 are constants that are our initial conditions of displacement and velocity. So our next step is to solve for W, because W is the square root of the spring constant divided by the mass. It's simply the square root of 64, which is 8. And now we have enough information to determine the general solution, which in this case is x of t equals c1 times cosine of 8t plus c2 sine of 8t. And our last step is to determine the specific solution. The problem told us that the initial velocity is 0 and also gave us the initial displacement was 0.2. First, the specific solution will just simplify to be 1/5 cosine of 8t. Thanks to Stuart Calculus and Paul the Calculus God at Lamar for saving my calculus grade. Yeah, that's all. Thanks for watching, peeps.